Okay, in the previous video we talked about the span of a set of vectors, and in this video we're going to talk about linear independence, which is in some sense a complementary idea to the concept of span. And span and linear independence are essential ideas in linear algebra. So I think when it comes to where students struggle with linear algebra, it's often in the section about span and linear independence. So definitely spend a lot of time thinking about these concepts, work with lots of examples, do lots of problems, and that should give you a good understanding of linear independence. And it's very important to understand this very well because pretty much every lesson from now on will involve the concept of span and linear independence. So if you don't understand it, it's really going to make it very hard to understand the rest of the class. Or, well, in this case, the rest of the videos. All right, so first let's define what linear independence means. So let's say that you have a bunch of vectors in Rn. Okay. Well, we know in the context of linear combinations, right? We saw that a linear combination is just when you take a scalar multiple of each of the VI's and then add them up. Now, what if you have a linear combination? So consider this equation C1V1 plus dot 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 plus CKVK. So this is your general expression for a linear combination equals the zero vector. Well, we know right away that, see, can you come up with values of C1 through CK that make this equation true? No matter what your V1 through VK are? Yes, there is. You can take C1 equal to 0, C2 equal to 0, dot, 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 all the way through CK equal to 0. So we know that if C1 is 0, C2 is 0, dot, 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 CK is 0, then C1 V1 plus dot 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 plus CK VK is going to be 0 V1 plus dot 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 plus 0 VK, and if you have 0 times a vector, that's just the 0 vector. So I'm just adding the 0 vector k times, and that's going to give me the 0 vector. So what that means is, so let's call this equation star. So C1 equals 0, C2 equals 0, dot, 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 through CK equals 0 is a solution to this equation star. The question is, so in other words, i.e., C1 equals C2 equals dot, 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 equals CK equals 0 implies that C1 V1 plus dot 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 plus CK VK is equal to the 0 vector, right? Now in general, it's not true that the reverse direction holds. So, right, this may or may not hold, okay? Right, may or may not be true. It may not be true that if C1 V1 plus dot 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 plus CK VK is the 0 vector, that means that C1 through CK is 0. It depends on what your VI's are, right? And that leads us to the definition that we're about to give, that V1 through VK are independent if the reverse direction is true. So let's give the definition. So we say that the set v1 through vk is linearly independent if the only solution to the equation star, which is above this equation, if the only solution to this equation is C1 equals 0, dot, 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 CK equals 0. In other words, i.e., this equation, C1 V1 dot, 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 plus CK VK is the 0 vector, implies, or it forces C1 to be 0, C2 to be 0, dot, 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 CK is 0. And otherwise, we say that, so let's just call this set of vectors S, just so that I don't have to keep writing it all the time. Otherwise, we say that S is a linearly dependent set. So notice that these are adjectives, linearly independent and linearly dependent, and they describe sets of vectors. So we say that the set of vectors is either linearly independent or it's linearly dependent, and it has to be one or the other, right? It can't be neither. So let's just spell out what it means to be linearly dependent. So S is linearly dependent if there exist scalars C1 through CK not all 0 such that C1 V1 plus dot 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 plus CK VK is the 0 vector. Now it may be that there are some of the CIs are 0, but to be linearly dependent, it means that there are scalars where not all of them are 0. Okay, so at least one of them is not 0. Right, let's just look at an example. Let's say that I have V1, which is 2, 3, negative 1, V2, which is 0, 0, 2, V3, which is 4, 6, 0, and V4, which is negative 6, 3, 1. So these are vectors in R3. Now it turns out that two V1 plus V2 minus V3 plus 0 V4 is the 0 vector. Okay. So what does that tell you about this set of vectors? So the set V1 through V4 is linearly what? What goes in the blank? Dependent. Right? Because I was able to produce scalars C1, C2, C3, and C4. So here your C1 was 2, here your C2 was 1, your C3 is negative 1, and your C4 is 0. Well, not all of those are 0, right? And I was able to produce this combination that equals the 0 vector. So therefore, by definition, the set is linearly dependent. Okay, so here you could figure out whether it's linearly dependent or independent if you knew this fact. I mean, we didn't talk about how we were able to get this fact, But if you think about it, if you're just told that this is true, then you know that the set is linearly dependent. I mean, you don't even need to know what these vectors are, right? If someone just told you that I have 4 vectors in R3 and this equation is true, then you know that this set is linearly dependent. Okay. So let's look at another example. Let's say I have V1 this is another example in R3. V1 is 1, 0, 0. V2 is 0, 1, 0. V3 is 0, 0, 1. Is this linearly dependent or independent? What do you think? We'll take a minute and think about it, and then we'll go over the answer. Okay, so let's go over the answer. The set V1, V2, V3 is linearly independent. Okay, let's justify this because, so what do we need to do to show that a set of vectors is linearly independent? From the definition, it says it's linearly independent if the only solution, okay, if you have this if you have this implication, right, that if you start out, if you know that C1 through Ck are scalars that make this equation true, okay, so you start with this, and you have to conclude that C1 through Ck are all equal to 0. So that's what you have to do. So if C1 V1 plus C2 V2 plus C3 V3 is the 0 vector, then what does that mean? Then C1 1, 0, 0 plus C2 0, 0, 1, 0 plus C3 0, 0, 1 is the 0 vector 0, 0, 0. And what does that tell you? Well, if you just read the equations, right, if you just read the equations that you get from this single equation, the linear equations, you get C1 plus 0 C2 plus 0 C3 is 0. I'm just going to even write it out all the way just to emphasize this. You get 0 C1, so this is 1 C1, and then 0 C1 plus 1 C2 plus 0 C3 is 0, and 0 C1 plus 0 C2 plus 1 C3 is 0, and then that's going to tell me the first equation just says C1 is 0, second equation is C2 is 0, third equation is C3 is 0. So if you know that this equation is true, right, that implies that all these coefficients are 0. So that tells me that there's no non-trivial linear combination of these 3 vectors, V1, V2, and V3, that produces the 0 vector. Let me just write that out above to indicate. So this solution, if you have C1 through Ck is 0, that's called the trivial solution to this equation. Okay. And if you have if there exists scalar C1 through Ck, not all 0, okay, such that C1 V1 through plus dot 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 plus Ck Vk is the 0 vector, that's called a non-trivial solution. To that equation. So in this case, this is, right, so in this case, C1 is 2, C2 is 1, C3 is negative 1, C4 is 0. This is a non-trivial solution to this equation. So if there is a non-trivial solution to the equation, the set is linearly dependent. Otherwise, if there is no non-trivial solution, only the trivial solution, then the set is linearly independent. All right, so those are some examples, some easy examples to illustrate the definition. And one thing to say before we go on is that when you look at the definition of linear independence, right, these adjectives, linearly independent and linearly dependent, describe a set. Okay, they're adjectives and they go with a set S. So you don't say a linearly independent matrix. Okay, a matrix is linearly independent. No, you don't say that. Okay, just never say that. It's a linearly independent set of vectors, and the matrix is very different than a set of vectors, right? A matrix is a matrix. Set of vectors is a set of vectors. They're totally different things. Okay, because I keep hearing students say linearly independent matrix, and it's not correct. Okay, and then another thing is that colloquially we'll say that if you have this set S, which is linearly independent, okay, colloquially we'll say that V1 through Vk are independent. Instead of saying that the set is linearly independent, okay? But when someone says that, right, when someone says V1 through Vk are linearly independent, it doesn't mean that each of the vectors is linearly independent. So this is something that has to do with like a quirk of the English language. I mean, if someone says the pencils are yellow or the bears are brown, right? What that means is each pencil is yellow, each bear is brown. But if someone says V1, V2, and V3 are linearly dependent, right? They're not saying V1 is dependent, V2 is dependent, V3 is dependent. I mean, that doesn't make any sense. It's the collection of vectors. It's the fact that you have this relationship. So in this example, it's the fact that you have this relationship among the vectors. That 2v1, in this example, it's 2v1 plus 1v2 minus v3 plus 0 v4 is the zero vector, right? That describes the collection v1, v2, v3, v4. So properly speaking, the word linearly independent, that term goes with a set of vectors. And it's not exactly correct to say that the vectors are independent or the vectors are dependent. On the other hand, everyone says that. So as long as there's no confusion about what we mean, then it's not a big deal. So, everyone says, okay, are these vectors independent? Are these vectors dependent? But what is proper is to say, is the set of vectors dependent or dependent? Okay. And they're not saying, is each vector independent? Is each vector dependent? All right, let's talk about, so if you have a general set of vectors, v1 through vk, how do you tell if the vectors are independent or not? So how to determine linear independence in general? So if someone just gives you these vectors, v1 through vk, how can you tell if the set is independent or not? Well, if you think about what we did in these other examples, and if you think about what linear dependence and independence is really saying, right? In this previous example, in this first example, you were given this relationship. This is called a linear dependence relation, by the way. A linear dependence relation is when you have a linear combination that's the zero vector and not all of them are zero. Not all the scalars are zero. Okay. So how do you know if there is a linear dependence relation or not? Well, each linear dependence relation gives you a way of solving C1 V1 plus dot 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 plus CK VK is the zero vector, right? And remember that, recall that C1 V1 plus dot 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 CK VK, right? That is what you get when you take the matrix whose columns are v1 through vk and you multiply it by the vector c1 through ck. So let's call this matrix A, right? The question is, and let's call this vector x. So then the question is, does ax equal 0 have a non-trivial solution? Right. If the answer is yes, then the set v1 through vk is linearly what? Dependent. If the answer is no, then the set v1 through vk is linearly independent. So if you look at this equation, ax equals 0, right, that's the homogeneous equation. That's a homogeneous equation because I have this b is the 0 vector. The homogeneous equation always has x equals 0 as a solution, right? But does it have a non-trivial solution? That's the question we want to ask. Non-trivial meaning x is not the 0 vector. Well, suppose that there was a non-trivial solution, right? That means that there's at least two solutions to your equation because you have x equals the 0 vector as a solution and your non-zero x is also a solution. And you remember if you have two solutions to an equation, and this is a system of equations with real coefficients, how many solutions do you have? You have infinitely many. Right. So this is the same as saying that ax equals 0 has infinitely many solutions. If it has a non-trivial solution, it must have infinitely many solutions. And when does ax equal 0 have infinitely many solutions? When the echelon form, what can you say about the echelon form? When there's a free column, right? So this is the same as saying that an echelon form of A has at least one free column. And if the echelon form of A, just any echelon form of A, has no free column, then ax equals 0 has only the trivial solution. Because remember, you need those free variables to produce the infinitely many solutions. So now we can determine the criterion, right? It's when you take your matrix A, this matrix, where you take your vectors v1 through vk and make them the columns, you row reduce, and then if there's at least one free column, then you know that v1 through vk are linearly dependent. And if the echelon form has no free column, right, every column is a pivot column. So in other words, i.e., there's a pivot in every column, then you know that the set is linearly independent. Okay, let's look at an example. Is this set linearly independent or dependent? And it's v1 is 1, 2, 3, v2 is 2, 5, 6. I mean, this is just a very easy example. But it's just to practice applying the criterion. We form the matrix A, which is the first column is 1, 2, 3, the second column is 2, 5, 6, and then you row reduce. So what's the echelon form of this? You do row 2 goes to row 2 minus 2 row 1. So you get 0, 1 here, and then row 3 goes to row 3 minus 3 row 3, 3 row 1. Let me just write this down. So it's row 2 goes to row 2 minus 2 row 1. Row 3 goes to row 3 minus 3 row 1, and you get 0, 0. Okay, hopefully at this point we're okay on how to do the row reduction. Remember, you just take the first number on the top left and you use that to make all the numbers below it equal to 0, right? So this is an echelon form of A. And when you look at it, how many pivots do I have? I look at the first non-zero number in each row. I have a pivot here and a pivot there. So I have a pivot in every column, and therefore, so since this echelon form of A has a pivot in every column, the set V1, V2 is a linearly independent set. Okay. Actually, we're going to figure out some criteria that will enable us to see right away that this set is linearly independent. But the point of this example is to show the general procedure, right? So if I give you, or if you're given a bunch of vectors and it's not very obvious whether it's dependent or independent, then you can use this algorithm. You just take your A, take the echelon form and see what you get, and that will tell you if the set is independent or not. Okay, let's do one more example. This is sort of like a test question. Find the values of K. Find the value or values of K for which the set 1, 2, 0, 1, 0, 1, 10, 41, K is linearly dependent. So pretend that this was like a question that you got on a test. So take a minute and try to figure it out, and we'll go over the answer. So pause the video because in a few seconds I'm going to go over the answer. Okay, let's go over the answer. So I have these vectors v1, v2, and v3 in R3, and I want to know what values of K, right, will make the set linearly dependent. So phrasing it in terms of this matrix, let's take this matrix A, formed by taking the columns, taking these vectors v1, v2, and v3, what am I trying to do? I want to row reduce, and I want, okay, so if there is a free column, if I get something with a free column, then my set is linearly dependent. If I get no free columns, then the set is linearly independent. Okay. All right, let's row reduce. So here I do row 2 minus 2 row 1, right? And that will give me, this first row stays the same, the second row turns to 0, so this row 2, 0, negative 2, 21, is that right? Yeah. And then 0, 1, K. Now at this point, I'm done with the first column, and so I have this submatrix here that I need to continue, and it's easier if I swap rows 2 and 3. So I'm going to swap rows 2 and 3 so I get a pivot of 1. And I'm almost at an echelon form. I want row 3 goes to row 3 plus 2 row 2. Oh, in this previous step, I'll just write out, I swapped rows 2 and 3. Okay. So now when I continue, I'm going to get 0, 0, 0, 21 plus 2k. Okay, so that's my, so here's my A, and here's my echelon form of A. And I want, so when I look at this, I see a pivot. Where are my pivots? Okay, I take the first non-zero number in the first row, that's this. I look at the second row, first non-zero number, and now this. Well, it depends, right? If this guy, this 21 plus 2k, if this thing is 0, then I do not have a pivot in this third row. I mean, this column does not, this third column will not have a pivot. So if that guy is 0, because remember, pivots are non-zero numbers. So if this is 0, then this third column has no pivot. If it is not equal to 0, then it's a pivot, right? So it's linearly dependent. So V1, V2, V3, this set is linearly, okay, since we're trying to figure out dependent, it's dependent if and only if echelon form has a free column, and that's true if and only if 21 plus 2k is equal to 0. And that's the same as k is negative 21 over 2. So the answer is negative 21 over 2. If k is negative 21 over 2, then I get an echelon form where the third column is not a pivot column. If k is not equal to negative 21 over 2, then I will have a pivot in every column, and so my V1, V2, and V3 will be linearly independent. Okay, so that's what I want to say in this video. So let's just review. I mean, there's more to say about linear independence, but let's just do a brief 1-minute summary. So we started by introducing this linear combination of vectors that is the 0 vector, and we just noted that if all the coefficients are 0, then you get the 0 vector. And our definition was that a set is linearly independent if that's the only way you can get the 0 vector, by making all the constants, the coefficients equal to 0. If it's possible so that not all of the CIs are 0, then the set is called linearly dependent. We saw some examples, this first example, which is a set of dependent vectors, and this other example, which is independent. And we talked about how to determine linear independence in general, and the idea was that this expression, this general linear combination, is what you get by taking this matrix A and multiplying by this vector C1 through Ck. So it boils down to whether this x, is it possible for your x to be not the 0 vector if ax is 0? And we translated independence and dependence to this criterion, and we saw that that's the same as when you find an echelon form of your matrix A, does it have a free column or not? And we did a few examples of this. Okay, in the next video, we're going to talk about a general way of thinking about linear independence. It might not be very intuitive, you know, don't be surprised. I mean, I don't expect this to make a whole lot of sense. I didn't really, not that it doesn't make sense, but it might not be obvious why we would care about this. Like, what's the significance? Why do we care about whether you get the zero vector as a linear combination, non-trivial linear combination? What is the significance of this? How is it relevant? Why is it important? We didn't really talk about that. That will be in a future video. We'll talk about the more intuitive way of thinking about linear independence. And we'll also see some quick ways of determining when a set of vectors is independent. It turns out that in some examples, you can tell right away whether your set is independent or not. In this video, we talked about the general method that works no matter what, but it can be time-consuming to row reduce the matrix. Sometimes you can tell right away that a set is dependent or independent, and we'll talk about that. Okay, thanks for watching.